In this video, I will show how to use Mlxplore to explore new simulations based on a model estimated in Mlx with different dosing regimens. In this Mlx project, I have estimated a simple two-compartment PK model on a dataset that contains PK concentrations measured in 20 patients after a single dose administration with different amounts from 5 to 20 milligrams. Now I would like to explore the behavior of this model for a multiple dosing regimen. I can do this easily by exporting the project in Mlxplore. This will reuse the elements defined in the project, such as the structural model and the initial estimates, to perform quick simulations. To use the population estimates from the results, I just have to record them as new initial values beforehand. So in the tab Initial Estimate, I click on Use Last Estimate and I save this modified project under a new name. I can then choose Export and export to Mlxplore. A pop-up window opens to set a grid for the simulation of the model and to select from which individual of the dataset the dosing information should come. I choose a fine grid with a step of 0.1, and to compare different doses, I select the individual 1, who has received a dose of 2 milligrams, and the individual 20, who has received a dose of 20 milligrams. An Mlxplore project is then automatically created. The definition of this project can be seen in the editor here. It contains the same elements as the Mlx project. In particular, the section Data File contains the path to the dataset and the definition of the columns. The section Model contains the definition of the individual parameter models, as well as the structural model with the observation model. The section Parameter contains the initial parameter values from Mlx. Finally, the sections Design and Output are specific to Mlxplore and contain the treatment designs and the variables and grid for the outputs. Here I can see the two treatments that I have selected, with a dose of 2 milligrams like the individual 1 and a dose of 20 milligrams like the individual 20. This script can be edited, so I will now replace the single dosing times by multiple dosing times. I can write with double points a vector of dosing times from 0 to 200 every 24 hours. I set the same dosing times for each treatment. I also increase the last time of the simulation grid until 250 hours. When I click on Run, the model is then simulated based on the population parameters, each of the two treatment designs and the outputs defined in this script, and the result is shown in the tab Graphic. I get one prediction curve per treatment. The residual error is not taken into account, but the inter-individual variability can be visualized by checking the box Random Effects as prediction intervals for the population. By default, only one curve is then showed, but I can display the second treatment again by clicking on the elements to show in the legend. Prediction intervals can be customized in percentiles. So based on this model, the concentrations for each dosing regimen should reach a steady state before 200 hours. Note that the simulations are not based on the dataset, but only on the model and parameter values. In data, the observations from the dataset can be overlaid for comparison by clicking on this box. Moreover, it is possible to change the dataset. In this case, I have an additional dataset with measurements of the same drug concentration on 10 individuals who receive 9 doses of 20 milligrams every 24 hours. I will now load this dataset in Mlxplore to check quickly whether my model estimated on single doses also matches this new dataset. So I click on Browse and I select my dataset. In this window, I can see the column headers in the dataset, and I just need to indicate which column is the time and which column corresponds to the observations Y. I can then check this box to overlay the data points on the plot. Here the dataset contains trough concentrations measured before each dose and dense concentrations after the last dose. I notice that the simulations for multiple 20 mg doses in gray do not match the measured concentrations, which decrease with time. This tells me that my model is not appropriate for modeling concentrations on long timescales with multiple doses, and that I need to adapt this model to take into account the decreasing troughs in the dataset. This decrease might be explained, for example, with a time-varying clearance. In conclusion, exporting a Mlx project in Mlxplore allows to simulate quickly the model and to explore modifications of these simulations, such as different dosing regimens.